Okay, we're looking at experiment 5. This is the speed of sound, and we're going to measure the speed of sound actually by looking at standing waves. Now, in the previous experiment, we looked at standing waves on a string. In this experiment, we're going to look at standing waves which set up in an air column. So this is a resonator where one end is open and the other end is closed. Now, the whole idea of calculating the speed of sound is to look at the frequency. We're going to use a tuning fork to generate a constant frequency, a little silhouette on that screen right there. And we're going to use the standing waves which set up, which have a very particular wavelength inside the, show you my experiment right here, inside this resonance tube right here. So hopefully I can keep everything in the video screen while I'm explaining this. So in any case, I'll go through this and then we can just look at the experiment a little bit closer. All right, so open, closed, and resonator. At one end of the resonator, we have a node where there's going to be no movement in the air. That's the closed end. In the open end, we're going to have an anti-node there. That's where the air is going to have its maximum amount of movement. So again, open end, anti-node, closed end, node. This is a little bit different from what we had with the resonator on the string, the resonator and the string. In that particular case, there are two nodes on either side. So you've got either one antinode at the center, two antinodes, three antinodes, so on and so forth. This is different because instead of being bound by two nodes, we're bound by an antinode and a node. So what kind of options do we have for standing waves? Well, if we have an antinode at the open end and a node at the closed end, we can simply have our lowest frequency, our fundamental, to be antinode node, where the length of the tube is actually 1/4 that of the wavelength, okay? So basically, if we look at the length of the tube for our first harmonic in this open-closed type of geometry, the wavelength is 4 times larger than the length of the tube. Now again, I'm going to adjust the size of the resonator by taking water and raising it up this column and lowering it down this column. All right, what else do we have here? Next option, if I have an antinode and a node, we've got to go through the full cycle. We've got to go node, antinode, and I've got to return through a node to an antinode to get to my next resonance, okay? That means that this is 1/3 the wavelength of what this was, okay? So here the tube was 1/4 the length of the wavelength. Here we are 3/4, okay? Then of course we can see how this pattern is setting up. 1/4, 3/4, 5/4, 7/4, okay? So again, a little bit different. When we did the wave on a string, basically all we had to do is, look at the size of the loop, and our wavelength was simply twice that size. Here, because our standing waves don't have nodes bound on each side of the tube, we have to consider this extra little antinode sitting at the open end. Okay, so again, we're going to look at these different resonances. We're going to look at these different types of standing waves. However, we are going to keep our frequency constant so that instead of being bound at some length, we are going to change the length to match whatever harmonic we have here. Now this is showing the case of our first harmonic, our third harmonic, our fifth harmonic. We don't have any even harmonics with this open closed tube here. And here the frequency is changing. We change the frequency to change the wavelength. Imagine the same thing, except we're taking this tube and stretching it out for the same frequency to be able to fit Antinode, node, antinode, node. All right? So again, here is our equation for what we get for the frequencies of an open-closed resonator. And you can see again, there's some number n, which is an odd integer, times the speed of sound, okay? Why the speed of sound? Because the way to relate the frequency to the wavelength, we've got to throw in the velocity. We divide that by 4L. And again, each harmonic is some integer value times the fundamental, okay? Now we're going to switch things up. What we're going to do is instead of keeping this changing, we're going to make our L change. So we're swapping these two out right here. And the length of the resonator for a particular frequency where we get a standing wave is going to go according to this equation right here. Okay? We can change this a little bit. I'm going to switch this out because, you know, dealing with odd integers doesn't work so well. What I'm going to do is I'm going to multiply this by 2 and add this, subtract this 1/2 off. And what that simply does here is it allows me to put a 1, a 2, a 3, or whatever in here, and replace all integers with what was originally just odd integers. Okay? Not really important for what we're doing because we're more interested in what the distance is between each of these resonances. It just makes later on when we're setting up our calculations easier to do. Now, there are a few different things we've got to consider here. One, the speed of sound changes with the air temperature. The air temperature right now in this room is 17 degrees Celsius, and therefore we use that to calculate our speed of sound. We're going to do this at the very end, where you can either use the equation which is given in the lab manual, or this equation right here, which we used in class to calculate temperature, velocity of sound, speed of sound as a function of temperature. Now here's the key thing. The speed of a wave is equal to the wavelength times the frequency. Speed equals wavelength times frequency, okay? That's really important here because that's really how we're calculating the speed of sound using standing waves. We know the frequency, it's going to come from a tuning fork. We know the wavelength. That wavelength is going to depend on the length of the tube and which resonance we're looking at. And again, those different lengths are from the previous equation, this right here. Okay, so why do we use a tuning fork? Well, the reason why we use a tuning fork is because tuning forks give off nice, fairly harmonic frequencies. They're not perfect, but they're fairly close. And when we strike it, I don't know how well you can hear this. You can hear the tone pretty well. Hopefully the sound from the microphones from the camera is picking it up. So I strike this and I try to see if this sound right here is going to be amplified by this cavity. All right. Of course, everything's in the wrong place right here. How this works is we have this reservoir can which has water. I can raise it or lower it, and that's going to cause the water to go up or down. Okay? So let me just show you that right here. I'm going to do a stop share so we can see this actually happening. And here is my setup. I'll move that to the center. And what you can see here, let me give the camera a little time to focus, is when I raise this up, you barely see the water going up. There's the water going up, there's the water going up. And when I let this down, the water goes down. All right. Now, I am going to raise this up, and I've already found my first resonance. Actually, it's up at 8 centimeters, but I'm going to try to find the second resonance right here. I put this little rubber band here to help me because, you know, as I'm doing this experiment, as I'm recording this, it's a little hard to operate everything that's going on here. But I want you to notice, I'll lower this down just a little bit. Okay, that's going to drop my water level below the resonance. I want to see if you can hear how the intensity of the sound changes as we go past the resonance. So again, this is a little bit slow. I'm going to raise the reservoir. You can see the levels going up, 19, 18, 17. Now my resonator is 16, 15, 14, and then I'm going to drop it. Hopefully I can do this fast enough. Let's see if we can hear this. Get a little louder. Okay, did you hear how it got louder right around 24? Probably rose it too quickly. Put it up too quickly. So we didn't get a good, we didn't get enough intensity. The tuning fork was already dying out, but I'm going to do it again. Now, hopefully it recorded pretty well there, but you can clearly see at that particular level, I got a fairly good response. Again, this is a resonator cavity. When I get a standing wave in there, it's going to amplify the sound coming from this tuning fork, okay? And you'll hear it get louder. So I heard it get louder at 8, heard it get louder at 24, and a few other places I'll show you when I show you my graph, okay? So let's go back to the PowerPoint. I love how we have these infinite screens right here. I'll go back to sharing. And once again, I'm going to share our little PowerPoint right here. And again, we can adjust the level by moving the can. And let me make one more change right here. I'm going to move our screen over to the, let's move it to the bottom. Hopefully I'll get a better case right there. And again, we can see the different resonances. If you want to see this full PowerPoint, I'm going to post it anyway. You can see here's where my first resonance was at 8 centimeters. Here's my other resonance at 24. If you can recognize the pattern, you can probably figure out where the next one would be after that. So what are we really looking for when we do this? We're looking for each resonance, L1, L2, L3. And then the distance between the resonances, what we call delta L, is going to be 1/2 the wavelength. So if I want to find the wavelength, I can just calculate it by multiplying the length by 2. Okay? All right, so delta L is equal to 1 resonance minus the previous resonance. It's twice, it's actually 1/2 the wavelength. I'll make that correction. Well, so again, the wavelength would be 1/2 that. All right, so when we're recording the data, you're going to record each resonance, all right? You're going to put its position, L1, L2, L3, L4, L5, L6. That's its position. We're going to do that in meters because we want everything SI. And then the difference will be the difference between L2 and L1. So here is my, let me get rid of the screen, or at least move the screen so it's smaller. I can move it up into this corner right here. And again, what we see here is I did 2 tuning forks. I did this twice. One tuning fork was at 1024. The other tuning fork's at 2048. And here are my different resonance numbers. 8 centimeters, 25 centimeters when I did this the other time. So the room might have been a little bit warmer when I did it the first time. 42 centimeters, 58 centimeters, 73 centimeters, 92 centimeters, okay? So you're gonna take the difference between these, okay? So for instance, 25 centimeters minus 8 centimeters gives me 17 centimeters, or 0.17 meters. Take the average of all your delta L's. It should all be around 17 centimeters. And then multiply that by the frequency. That will give you the wavelength once we multiply that by 2. Okay? So again, this delta L represents half the wavelength. Right? So if I multiply this by 2, I would get 0.34 for a wavelength. 0.34 times 1024. What does that correspond to in terms of a speed? Okay? So here's my delta L average. Multiplied by 2, that gives you your lambda. Multiplied by the frequency, that gives you velocity. And again, I also did this for 20, 48 hertz. So twice the frequency, half the wavelength. And notice that pretty much corresponds to half the values that I got before. Right? Get those differences. Again, the difference here is you'll get half the number. You're going to multiply this by 2, twice the frequency. That'll give you your new speed of sound. All right? Now, I apologize I couldn't perform this experiment in front of you and do each resonance. It's a fairly tedious process, and doing each one really would be very difficult for just a single person to do. Okay, once you're done with all your different calculations, you'll get a speed of sound for the first frequency. You'll get a speed of sound for the second frequency. You then want to take those speeds, should be around 340, 350 meters per second, if I did the experiment correctly, and compare that to the speed of sound calculated simply by the temperature. Okay? So this is another experimental way to calculate the speed of sound. Here, I take the temperature of the room, 70 degrees Celsius, multiply that by 0.6 plus 331.5, or you can use the previous equation that I showed you. And this is going way back. Here we go. You can use this equation too. That'll give you a pretty good answer also. All right. That's about it. Again, you're going to compare this speed to the speed that you got in the first case, this speed to the case that you got earlier. Remember, everything here is an experimental value. If we have an actual value, then we can compare that to an experimental value, okay, and do percent error. This is percent difference. We're comparing one experimental value to another experimental value. All right, that's it. Good luck.